Okay, so today we're working on section 1-3, define and use probability. So now you've done a little bit of probability with permutations and combinations. Now we're getting to kind of more specific probability of something happening or not happening. We can also call that the odds. So let's do some definitions first. The outcome of an event is a possible result, anything that could result from an experiment happening. Okay, so if you're going to roll a dice, the possibility is you're going to roll a head or a tail. If you flip over a card, it's going to be either red or black. It's going to be between an ace and a king. It could be a club, spade, diamond, heart. There's lots of different possibilities. An event is a set of outcomes. So for example, if you flip 5 cards over, if you turn 5 cards over, turn, okay. All right, a sample space is the set of all possible outcomes within an experiment. Results. Okay. And the probability of an event is the likeliness of something happening within that experiment. So the likeliness that out of 4 flips of the coin, how many times are you going to hit 4 heads in a row? How many times are you going to flip 2 heads and 2 tails? Okay. The likeliness of a specific outcome within a sample space, so within that experiment. Okay. All right, so probabilities are always out of 100%. This is 100% that it's going to happen every time. This is 0%. Halfway in between would be 50%. Okay? So anything from 51 on up to 100, the event is more likely to occur. Between 0 and 50, it's less likely to occur. You will often see probabilities in the form of fractions. So it'll say 4 out of 10 times. That means about 40% of the time. You'll see why the fraction thing comes in just a minute. When all outcomes are equally likely, the theoretical probability that event A will occur is the probability of, sorry about that, probability of event A happening divided by all the possible outcomes that could happen. Okay, so if you have 7 events that have happened, and event A is what you're looking for, that only happened 3 times out of 7 in this little diagram. Okay? Okay, so let's do some practice problems for that. So, and this is the part of probability of stat sets actually fairly straightforward. So, you pick a card from you pick a card from a deck of 52 playing cards. Find the probability of picking an 8, and then we're going to do picking a red king. Okay? So in a deck of 52 cards, 4 of those cards are 8s, right? You have 1 from each suit, out of a total of 52 cards. That's your probability. We always need to reduce it down. So the probability of choosing an 8 out of that deck would be 1 out of 13. Okay? For one time that you do choose an 8, 12 times you would not choose an 8 on average. That's the probability that would happen. Okay, picking a red king. Well, how many red kings are in a deck? There's the king of hearts and the king of diamonds. So 2 out of those 52 cards are red kings. Reduce that again, so the probability would be 1 out of 26. Okay. You have an equally likely chance of choosing an integer from 1 through 20. So already I know I have 20 options there. Okay. Find the probability that a perfect square is chosen. Of course, you know your perfect squares by now, so let's list out the perfect squares that happen between 1 and 20. So you have 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, so we don't need that one. So 4 out of those first 20 numbers are perfect squares. So again, we need to reduce. So 1 out of every 5 is a perfect square. Let's figure out the probability that a factor of 30 is chosen. So let's list out our factors of 30. So we have 1, 2, 3, 5, 6, 10, 15, and 30. So that multiplies to 30. 2 times 15 is 30, 3 times 10 is 30, and 5 times 6 is 30. Okay? So that's 1, 2, 3, 4, 5, 6, 7, 8 different options that we have out of the 20 numbers that we chose. So reducing that again, those both reduce by 4, so you get 2 over 5. Okay? So on to page 2. I realized in getting ready to do these notes that these 2 examples really should probably be put in the permutation section. Examples 3 and 4 should have been put in the permutation section because they have more to do with order. And so I'm going to have you on your notes skip this part for now, and we're going to come back when we're doing permutations. We'll worry about this. So I need you to skip down to the bottom of the page. And the item that measures the chance in favor of an event occurring against the chance, that should be chance, against an event occurring would be the odds. A lot of times you'll see this when you talk about any kind of gambling. They're always talking about the odds. What are the odds you're going to win the lottery? What are the odds you're going to win at blackjack? What are the odds of a horse on a horse race? This is kind of what the entire gambling industry is based upon. Excuse me. So the odds in favor of an event or the odds against an event. When all outcomes are equally likely, the odds in favor of an event A and the odds against an event A are defined as the following. So it's basically the number of times you succeed versus the number of times you would fail. It's really what it is. So you really could write that as success and failure. Flipping that again, you could have that your failure to your success rate, right? That's really a way to look at it too. Okay? So if we're going to do that, say the odds of a horse winning a horse race were 5 to 2. That means 5 times he's going to win that race and 2 times he's going to lose that race, based on the horses he's running against, based on all the things that they put into making odds on a horse. So you can either write that as 5 to 2 or 5:2, like that. Okay, that was a short page of notes because we decided to move that. Let's go on to page 3. So a marble is drawn from a bag containing 6 red, 12 yellow, and 9 black marbles. Find the odds in favor of drawing a red marble. Okay, so total, we need to know what we're drawing. We're trying to get a red, but the total that we need is the red plus the yellow plus the black. Okay, so we have 6 red marbles. In total, we have 6 plus 12 yellow plus 9 black marbles. So 6 on top, and we have 18 plus 9 is 27. So out of those 27 total marbles, 6 of them are red. The chances that we're going to pull one of those, we need to reduce those each by 3, so we get 2 out of 9. Okay? For every 2 red marbles I pulled, 9 of those marbles are not going to be red. Those are the odds. So that's about a 22% chance. So you'll put your hand in that bag and take out a marble and it will be red. Okay? Find the odds against drawing a black marble. So success is not drawing a black marble. Think about what colors you could draw. So that means you're either drawing a yellow or a red marble. Okay, so we still have 27 in the bag, 6 are red, 12 are yellow. So 18 out of the 27 are not black, and we can reduce that down to 2/3. So there's about a 67% chance that you're not going to choose a black marble. Okay? So for experimental probability of an event, when an experiment is performed that consists of a certain number of trials, so you roll a dice 5 times, you choose 5 cards from a deck, you flip a coin 10 times. That's the certain number of trials. The experimental probability of event is given by the number of times event A, we're using A here, event A occurs. Let's extend that line all the way out, and out of the total number of trials. Okay. So, and that should make sense to you. If you flip a coin 10 times and they want to know how many times you flip ahead, and you flip ahead 3, then that's a total number that the event A occurred over the total number of trials that we did. We flipped that coin 10 times. Okay, so blood type for sample donors at a blood driver given in the bar graph below. Find the experimental probability that a randomly selected blood donor would have blood type O. So we're looking at blood type O right there. So we know that we're looking at 22 out of the total. Now we have to figure out the total between this. So we have 22 have type O, 21 have type A, 5 have type B, and 2 have type AB. So let's total those up. We have 22 and 21 is 43, 48, 50. So out of that, we have 11 over 25. Example 7, the bar graph shows how old adults in a survey would choose to be, let me rephrase how I'm reading that. The bar graph shows how old adults in a survey would choose to be if they could choose any age. Find the experimental probability that a randomly selected adult would prefer to be at least 40 years old. So I want you to think about what at least means mathematically. So that means that it can be greater than 40. They also can be equal to 40. So when you're looking at your chart, it's everything from here to the end, between 40 and 49, 50 and 59, 60 and 69. So we need to total up those 3 possibilities, because that's where all of our valid ages lie, over all of our possibilities. So it should be this complete, all of these numbers for every age range. So you'd have 463, 1085, 879, 551, 300, and 238. Okay? Once you get those totaled up, you should have 1089 over 3516. For our purposes right now, I'm not going to get really hung up on simplifying that large number right there. It is actually reducible by 3, so let's do that. So it goes in 363 over 1172. I don't think it can reduce farther than that. So that's your reduced fraction there. I knew that it reduced by 3 because 9 plus 8 plus 1 is 18. That's divisible by 3. 6 plus 1 plus 5 plus 3 is 15. That's divisible by 3. So each one of these can be reduced by 3. Okay, and that was the end of section 1-3. Very short. We'll do a lot of practice on these in class. And section 1-4 is coming right now.